You want to do the intro?
No, I'm good.
You're good? All right. 2.7, graphing techniques. Talk about stretching and shrinking, also known as compressing. We're going to reflect graphs. We're going to talk about symmetry. Symmetric about the x-axis, symmetric about the y-axis, symmetric about the line y equals x. There's all kinds of symmetry. Even and odd functions, and then translations. Translation means, what's a translation? What's a translation? Starts with an SL. A translation. Slide. I can slide it up. I can slide it down. I can slide it over. It doesn't change shapes. It's a slide. Okay. What's a reflection? It's a flip. Reflection is a flip. Yeah. Good stuff. Consider the graph y equals a times f of x and y equals f times a of x. We're going to compare the graphs of those functions where a is positive. Yay. Graph each function compared to the parent function. Okay, so we're going to graph the function 2 times the absolute value of x. But before I graph g of x, which is 2 times the absolute value of x, I'm going to start by graphing the parent function of that. And what is the parent function of 2 times the absolute value of x? Just the absolute value of x. Okay? Absolute value of x. We're going to graph that. And what's the absolute value of x look like? A v, vertex at the origin, slope of 1 and -1. We're drafting, Jordan? Okay. Well, just a friendly reminder, 6th period is the class that actually is more involved than my other classes. So. All right, now let's graph 2 times the absolute value of x. What is that 2 going to do? Anybody remember? It's going to be one of those. Okay. Am I changing the value of x, or am I changing the value of the function? The function is absolute value of x. Am I changing the absolute value of x because it's 2 times the absolute value of x, or is it 2 times x? It's 2 times the absolute value of x. So I'm changing the function. Follow me here. I'm changing the function. I'm changing the function, which is the y value. The y value is changing. So this thing is changing vertically. How is it changing? Okay. So if I had, here's my f of x, and here's my g of x. If I plugged in -3, the absolute value of -3 is 3, and 2 times 3 is 6. So I'm going to plot the point -3, 6. -3, 6 is right here. Plugging in -2. F of x is the absolute value of that. The absolute value of -2 is 2. The g of x is 2 times that, so 4. So I'm going to plot the point -2, 4. -2, 4 is right here. Plug in -1. Absolute value -1 is 1. Multiply by 2 is 2. We'll plot the point -1, 2. I missed that last point, didn't I? I know. Plug in 0. Absolute value of 0 is 0. 2 times 0 is twice your, 0. Plot the point 0, 0. And we can continue this. I'll do one more point. Plug in 1, 1, 2. So what happened? How does that red graph compare to the blue graph? It got steeper. Okay. The value of y changed. The value of y looks like this. It now looks like this. I'm holding a gummy bear's feet in my hands. I grab the gummy bear's head and I pull it vertically, and what happens to that gummy bear? Before it snaps, it stretches and gets skinnier. It's a vertical stretch. Okay? Again, I changed the value of the function. By changing the value of the function, I'm changing the y. So whatever happens, I'm talking about vertical. I have stretched it vertically. Questions or comments or anything on this guy? Yes, sir.
Yeah, okay, so the f of x is just like the absolute value of x. It's nothing special.
Well, the special part about it is it's the parent function.
Okay.
So when I'm asking about what happened to the parent function, what happened to the original graph of absolute value of x? Well, what happened to it is it stretched vertically by a factor of 2. Okay. Other questions? Okay. We're going to graph h of x, which is 1/2 the absolute value of x. I still want to compare it to the parent function. My parent function is still going to be f of x equals the absolute value of x. That function is still at 0, 0, with a slope of 1 on the right side, a slope of -1 on the left side, forever and ever and ever. So for part B, are we changing the function or are we changing the x value? We're changing the function. We are changing the y direction. Okay? So again, we can make our table. I'm going to use nicer numbers. If x is -4, the absolute value of -4 is 4, and that point is already plotted at -4, 4. Half of 4 is 2. So h of x has a point at -4, 2. Plugging in -2, absolute value of -2 is 2. Half of 2 is 1, giving us a point at -2, 1. Is anyone not following me as I'm making these points? Does anyone not understand how I'm choosing values of x? Okay. For the absolute value function, what is the domain? All numbers. So I can choose any x that I want. Okay. I'm not going to choose 70 because it doesn't fit on my graph. I'm not going to choose 7/8 because I don't want to plot fractions. Right? But I can choose any values that I want. All right, plug in 0. Absolute value of 0 is 0. Half of 0 is 0. And I'll do one more. 2. Absolute value of 2 is 2. Half of 2 is 1. Can we draw our graph from that? You can clearly see the minimum. You can clearly see it's decreasing until it gets to the origin. From there, it begins to increase at a rate of up 1 over 2. Okay. What did the 1/2 do for this graph? A vertical compression, but in this text and this homework, it's not going to call it a compression. It's going to call it a shrink. We have a vertical shrink by a factor of 1/2. Every y value was cut in half. X value stayed the same. Was everybody done with that one? Good? Okay. One more. I'm going to graph k of x. K of x is the absolute value of 2x. Am I changing the value of x, or am I changing the value of the function? I'm changing the value of x. So now I'm messing with it horizontally. Okay? And I'm going to tell you, this graph is going to look an awful lot like one of the graphs we already did. Okay? We'll start off by comparing it to the parent function. Parent function, f of x equals absolute value of x. And now we'll do our g of x. So we have x, f of x, g of x. When x was -3, the absolute value of -3 is 3, but we're not changing the value of that, are we? G of x is 2 times x. What is 2 times -3? And the absolute value of -6 is? So -3 is 6. Plug in -2. The parent function has a plot at -2, 2. Take 2 times -2. Get -4. Absolute value of -4 is 4. I have a point at -2, 4. Is this graph looking familiar? Tiny bit? Looks like part, doesn't it? Okay. So -1 went to 1 for the parent function. Multiply it by that 2. -1, 2. And I'm just going to go ahead and plot some more points and graph it. Okay. How did this graph change compared to the parent function? Okay. What did the x change or the function changed? So it changed in the horizontal direction. It was here, it came in. So what happened to it? No. It's a horizontal compression. Okay? Because we changed the x value, it got smashed in. So it's a horizontal compression. Well, a compression times 2, that doesn't make sense, does it? Remember when we were doing translations, moving left and right? If it was inside the parentheses, it was opposite of what it appeared to be. This is inside, okay? This is a horizontal compression, but this text uses shrink by a factor of. Okay, shrink gets smaller. In my mind, 2 doesn't make things smaller. 2 doubles. 2 makes it bigger. But what's the reciprocal of 2? 1/2. It is a horizontal shrink by a factor of 1/2. So when you're changing the x value, that coefficient, you're going to take the reciprocal of it. the reciprocal of the coefficient on x. But this graph looks exactly like the graph of 2 times the absolute value of x. So a horizontal compression of 1/2 and a vertical stretch by a factor of 2 are essentially the same. But what you have to pay attention to is x changing or is the function changing. That way you get your direction correct. Clear as mud? Okay. Questions on this? Okay. Vertical stretching or shrinking of the function. If a is greater than 0, if a point xy lies on the graph of f of x, then the point xay lies on the graph. So if you know the original point, if a is greater than 0, you're going to multiply the y value by a, and that's going to be your vertical change. Notice the y value is changing. The function is changing. The function is multiplied by some number a. If a is greater than 1, then it's a stretch. If a is between 0 and 1, then it's going to be a shrink. Half of something, 2/3 of something. Obviously, that's smaller. Okay. Couple pictures there for you. Questions, comments, or anything on this? Okay. Horizontal. When we have a horizontal change taking place, the x is going to change. But look at that. Instead of multiplying x by a, we're dividing it by a. That's why it's the reciprocal. Dividing by 2 is the same thing as multiplying by 1/2. Okay? So again, in this case, we're changing the x value. We're not changing the value of the function. So y stays the same. X changes by dividing by that coefficient in front of the x. If a is between 0 and 1, then it's a horizontal stretch. 1/2 is a horizontal stretch because you're dividing by 1/2. Dividing by 1/2 is the same thing as multiplying by 2. If a is greater than 1, then it's going to be a horizontal shrink. So let me state this. I understand that a vertical stretch and a horizontal compression graphically can be the same thing. However, if it's a horizontal compression and you tell me it's a vertical stretch, that's wrong. Okay? Questions? None? Okay. Now this is a long section here. Reflections. Forming the mirror image of a graph across a line is called the graph across a line. Yay. Graph the function, compare it to the parent function. G of x equals negative square root of x. What is the parent function? F of x equals the square root of x. That's the parent function. Can you take the square root of a negative number? No. The domain of this guy is from 0 to infinity, right? Square root of 0 is 0. Square root of 1? 1. Square root of 4? Square root of 9? All right. So here is the parent function. We plugged in 0. The square root of 0 is 0. Looking at g of x, are we changing the x value? Are we changing the input? Or are we changing the output? Are we changing the value of the function? We're changing the output. We're changing the y value. So because the y value changes, we're changing it vertically. Okay? So if x is 0, the absolute value of 0 is 0, and negative 0, the opposite of 0 would be 0. That was hard. Plug in 1. Or not. All right, let's do that then. Okay. Absolute value of 1 is 1. The opposite of 1 is negative 1. So 1, negative 1 is on this graph. Plugging in 4. And understand that I'm plugging in perfect squares, right? I'm making life easy for me and you. What's the square root of 2? 1.414 approximately. Oh, wait, anyway. Square root of 4 is 2. Opposite of 2? Negative 2. So 4, negative 2. 4, negative 2. And one more, 9. Square root of 9 is 3. Opposite of 3 is negative 3. 9, negative 3. And there it is. Okay? What happened? We have a reflection across the x-axis. Notice that the x values are all the same. The y values changed. Right? Next graph. H of x equals the square root of negative x. Compared to the parent function. Am I going too fast for anybody? Is everybody okay? Okay, remember to slow me down if you need to. Okay. Parent function again is f of x equals the square root of x, which we know looks like this. So here's my x, my f of x, my h of x. So if I plug 0 in, first of all, what's changing? The input or the output? Input's changing. X is changing. So we're going to change horizontally. Okay. If I plug 0 in, we know that the function, the square root of x, the square root of 0 is 0. That goes there. But if I come over here, I plug in a 0. The opposite of 0 is 0. And the square root of 0 is? Okay, so I still have a point at 0, 0. Change colors. One second, let me change some stuff to red here so I can have these different graphs. Okay, if I plug a 1 in, if I plug a 1 into my parent function, I have the square root of 1, which is 1, and that point's plotted. But if I plug a 1 into my h of x function, I have negative 1. And the square root of negative 1 is undefined. So I can't plot that point. And it doesn't matter what numbers I choose for x that are positive, I'm going to have the same problem. Because every time I'm going to take the opposite of that value and plug it in. So let's go ahead and go the other direction. if I plug in a negative 1? Well, if I plug a negative 1 into my parent function, I have the square root of negative 1, which is undefined. But if I plug negative 1 into this, I have negative negative 1. What's negative negative 1? 1. And the square root of 1 is? So I have a point at negative 1, 1. Let's go to negative 4. Parent function, the square root of negative 4 is undefined. But when I plug negative 4 into h of x, negative negative 4 is 4. Square root of 4 is 2. So the point negative 4, 2 is on the graph. And I can do the same thing for negative 9. Negative 9, 3. So here is that graph. I missed the first point, but you get the idea. So the input changed. This is a reflection across the y-axis because it's changing it horizontally. It's changing the x values. Questions, comments, concerns there? Yeah, okay. Reflecting across an axis. The graph of y equals negative f of x is the same as the graph of y equals f of x reflected across the x-axis. I'm changing the y value. I'm changing it vertically, so because I'm changing it vertically, it's reflecting across the x-axis. If point xy is on the graph, then the point x negative y is on the graph. It's going to reflect the y. If the graph of y equals f of negative x, I'm changing the x value, is the same as graph of y equals f of x reflected across the y-axis. I'm changing it horizontally. Because I'm changing it horizontally, it's reflecting across the y-axis. The graph below is cut in half by the y-axis. This is symmetry. The blue half and the red half are mirror images. You could fold them in half and they'd be laid on top of each other. Okay, that is symmetric about the y-axis. This graph is symmetric to the y-axis. In general, for a graph to be symmetric with respect to the y-axis, the point negative x equals y must be on the graph whenever the point xy is on the graph. And we're actually going to do some math with this in just a moment so you can see this taking place. You do not want to graph every possible graph to see if it's symmetric. That's way too much work, plotting points. Okay? Here's a graph that's reflected across the x-axis. So if we folded it vertically, it's a reflection across the x-axis. Okay. The graph of an equation is symmetric with respect to the y-axis if you replace x with negative x and get the same thing. Okay? If you replace x with negative x and you get the exact same equation you started with, then it is symmetric about the y-axis. If, however, you replace y with negative y, that makes it symmetric about the x-axis. What if it was symmetric about both? Okay, that's going to happen here in a little bit. Okay, test for symmetry with respect to the x-axis and the y-axis. So what I want to do is I want to replace x with negative x. So if I do that, I get y equals x is now negative x squared plus 4. All I did was change x to negative x. Okay. What's the answer to negative x times negative x? Negative x times negative x. Because a negative times a negative is a positive. So this is equal to y equals x squared plus 4. Right? So this is a very simple problem. I plugged in negative x and I simplified it. How does what I simplified compare to the original? They're the same. So because f of x equals f of negative x, that's what just happened. This is a true statement. This is symmetric about the y-axis. I'm going to go back to the previous slide and read this first statement. A graph of an equation is symmetric with respect to or about the y-axis if the replacement of x equals with negative x results in an equivalent equation. Is that what just happened? Okay. So there it isn't happening. B. What would happen if I replaced y with negative y? I get x equals negative y squared minus 3. What's negative y squared? Y squared. I got the exact same thing. Right? Okay. Previous slide again. Sorry, I hit the wrong button. The graph of an equation is symmetric with respect to the x-axis if replacing y with negative y results in an equivalent equation. And I'll pick up there tomorrow.
Make sure to like and subscribe to our. There's at least one person.